Hello, Pre-Calculus Honors. We're still in Unit 13, Limits, and today we're going to talk about some special trigonometric limits. So to get you warmed up, we're going to look at the following limits right here. The first one in the do now is, what's the limit as x approaches pi over 4 of sine of x? Now you all know that sine of x just goes up and down and up and down. There's nothing special going on. There's nothing too exciting going on at pi over 4. There are no asymptotes. There are no holes. So basically for a trigonometric limit, we just plug in. So that limit is going to be equal to whatever sine of pi over 4 is. You've got to know your speed chart at this point, so if you don't know it, go back and rememorize it. But the sine of pi over 4 is rad 2 over 2. And of course, we're looking for an exact value, not a decimal approximation. We can use this same technique when we look at the limit as x approaches 2 pi over 3 of cosine x minus x. So again, nothing special going on at 2 pi over 3 in terms of the cosine function. So we're just going to plug in. So it's going to be the cosine of 2 pi over 3 minus x, which is 2 pi over 3. So we evaluate the cosine of 2 pi over 3. The cosine of 2 pi over 3 is the same thing as the cosine of pi over 3, which is the cosine of 60 degrees, which is 1/2. But in the second quadrant, which is where 2 pi over 3 is located, it's going to be negative 1/2. All students, only sign is positive there. Minus 2 pi over 3. And that's about as pretty as it gets. We could get a common denominator, but don't bother. So what happens if we've got a problem like this? What's the limit as x approaches 0 of sine x over x? Now this is a lot more exciting because if you try to plug in 0, you will get 0 over 0, which is an indeterminate form. Now we've already looked at this in a previous lesson. We looked at it on the calculator. We got closer and closer to 0 from both sides, and we realized that that limit is going to be 1. So this, you're just going to have to memorize. The same thing with the limit as x approaches 0 of 1 minus cosine x over x. Again, if I try to plug in 0, I will get out 0 over 0. And I promise if you take a look at it on your calculator, you will see that that limit is actually 0. So if we could take these two special trigonometric limits and kind of manipulate them to turn other limits into this type of form, or at least part of it, then we'll be able to evaluate other trigonometric limits that look like we can't answer right away by just plugging in. I do want to point out that both of these approach 0. If x is approaching anything other than 0, these two special trig limits don't hold true. So let me show you what I mean. So let's say we want to evaluate the limit as x approaches 0 of sine of 4x over x. Now if I try to plug in 0, 4 times 0 is 0, sine of 0 is 0 over 0. So I get an indeterminate form. Now my special trigonometric limit works as long as the argument, whatever's inside the sign, is exactly the same as what I'm dividing by. So in the previous one we had x over x. So this is 4x over, if I can make this a 4x, then this is my special trig limit. Then that piece is 0. So basically if I put a 4 on the bottom, the way to balance that out is I need to also put a 4 on the top. So my answer is going to be 4 times the sine 4x over 4x is just going to be 1. The answer to this problem is 4 because I kind of maneuvered it, I manipulated it, so I got my special trig limit in there. Let's do the same thing with the next one. Sine of 6x over 5x. Again, the argument, what's inside the sign, is 6x. So I need the denominator to also be a 6x. So what could I multiply 5 by to make it a 6? Well, I could multiply it by 6/5. Now it's a 6x. So now this is just 1. And I need to put a 6/5 on top to keep it balanced. So I've got 6/5 times 1, which is just going to be 6/5. Okay, how am I going to play around with this one right here? I've got a sine squared x over x squared. Again, I'm trying to turn it into a form where I've got sine x over x, or sine of nx over nx. So let me split that sine squared into sine x times sine x, because that's of course what sine squared is. And if I split the x squared into x times x, you'll notice this piece right here is 1. This piece right here is 1. And because of our properties of limits, if I've got the limit of a product, that's just going to be the product of the two limits, which will be 1 times 1. So the answer to that problem is just 1. So I'm able to now evaluate some limits that I couldn't evaluate just by plugging in. Okay, our next example is, what's the limit as x approaches 0 of tangent x over x? Again, if I try plugging in, I get 0 over 0. Now this one isn't as apparent, but I know that you all remember that tangent, of course, is just sine over cosine. So I'm going to rewrite tangent as sine x over cosine x. And I'm going to multiply that by the 1 over x that I've already got, this piece right here in the denominator. So right now, I can basically say I've got my sine x over x. I know that that's equal to 1. So if I try plugging in right now, I've got the limit as x approaches 0 of 1 over cosine x times sine x over x. Again, this piece right here we know is 1. So if I just try plugging in 0 into the 1 over cosine x, 1 over cosine of 0 is 1. I get 1 over 1, so that's going to be 1 times 1. This limit is also 1. So I'm just manipulating my limits until I can kind of pull out one of my special trig limits and then evaluate what's left over. Well, for this one, I've got the limit as x approaches 0 of sine of 3x over sine of 4x. I need that 3x to have a 3x in the denominator. So if I put a 3x in the denominator, I better put a 3x in the numerator. And I need the sine of 4x to have a 4x in the numerator, so I better put a 4x in the denominator. I should have mentioned earlier that it doesn't matter if the sine of x over x is in the numerator versus denominator, or if it's x over sine x. Either way, that limit's going to be 1. So I've got the sine of 3x over 3x. That's just 1. And I've got 4x over the sine of 4x. That's also just 1. So I've got a 3x on top and a 4x on the bottom. I hope you all realize that I can cancel the x's. So if I kind of rewrite this, I've got the limit as x approaches 0 of sine of 3x over 3x. I know that's going to be 1. Times 4x over sine of 4x. I also know that's going to be 1 because that's just the reciprocal of my special trig limit. Times, I've got a 3/4. So again, I can just do the product of their individual limits. So that's going to be 1 times the limit of 3/4 is just 3/4. That's a constant. So the answer to this problem is 3/4. Okay, we've got the squeeze theorem here. We're going to wrap it up with the squeeze theorem. This is a nice short video tonight. And it basically says this. Suppose that for all x on the interval a, b, including a and b, except possibly when x equals c, we have that f of x is less than or equal to h of x is less than or equal to g of x. So I've got 3 separate functions. F of x is the smallest function, h of x is kind of the one in the middle, and g of x is going to give us the largest y values in their function. Also suppose that we've been told that the limit as x approaches c of f of x is the same as the limit as x approaches c of g of x, and that value is just L. And that holds true for some number c that's located between a and b. The squeeze theorem says, since c is somewhere between a and b, the limit as x approaches c of h of x, that middle function, will also be L. Now the easiest way to understand the squeeze theorem is to take a look at it. So we've got this. F of x is our lowest function, it's green. H of x is that function in the middle, that's blue. And g of x is kind of our upper function. And I said that g of x is larger than or equal to h of x, which is larger than or equal to f of x, except they could be equal to one another. So say that they're equal to each other at c, because then the limit as x approaches c of g of x coming from both sides will be L, and the limit as x approaches c of f of x coming from both sides will also be c. So since h of x is kind of in between the two of them, that limit must be the same as well. So here's an example of the squeeze theorem that I just kind of threw together. Let's say we've got a function f of x is equal to x squared plus 2, and another function g of x is equal to 2 minus x squared, and I'm going to tell you that f of x is greater than or equal to h of x, which is greater than or equal to g of x. So this time f of x is our larger function, g of x is our smaller function, and h of x is somewhere in between the two. And the question is, even though I don't know what h of x is, can you evaluate the limit as x approaches 2 of h of x? So let me draw a quick little sketch here. You all know that f of x, let's make that red, x squared plus 2 is going to give you an upward facing parabola shifted up 2. So there's my f of x right there. And I've also got some function g of x, which is 2 minus x squared, which is an upside down parabola that's going to pass right through there. That's going to be my g of x. I have absolutely no idea what h of x is, but I do know that it's somewhere between f of x and g of x for all values between a and b, whatever those values are. So what's the limit as x approaches 2 of h of x? Actually, this should have been, let's fix that, please. This should have been the limit as x approaches 0. And you can see why. Because 0 is where these two functions are basically being squeezed together. Since the limit is as x approaches 0 of f of x is 2, and the limit as x approaches 0 of g of x is also 2, then the limit as x approaches 0 of h of x must be 2 because it's between the two of them. So if we have any questions on this one, we'll go over this tomorrow in class. I'll see you then.